So as you remember, we had this result here last time, that the definite integral of a function can be evaluated using the antiderivative of the function, assuming the function has an antiderivative. So here, rather than doing the limit definition of this definite integral, here the definite integral of capital F prime, we can use the antiderivative of F prime, which is F, to calculate the definite integral. So that was the whole, big kind of breakthrough with the evaluation theorem, that it saves us all this trouble. We don't have to worry about Riemann sums anymore and all that kind of stuff. And so here on this slide, we did a brief interpretation of what the integral of a rate of change meant, and we interpret that as a net change. And one very important application is to density. And, I'll let you take a look at that again. And the thing I highlighted was using the units to determine what the integral is calculated. So I wanted to come back here and mention again the idea of the so-called dummy variable in a definite integral. The reason this is important is because the dummy integral plays a significant role in the fundamental theorem of calculus part 1, and it's a potential source of confusion. So that's why I want to talk about it a little bit before we get to the fundamental theorem of calculus part 1, which we will get to today. So here, you should take a look at, we have a definite integral of the integrand here is f prime of x dx. So according to the evaluation theorem or fundamental theorem of calculus part 2, this integral will equal f of b minus f of a. And so the point I want to now emphasize is b is a constant, a is a constant, so that this entire expression is a constant. There are no variables in this integral. This integral here is equal to the constant f of b minus f of a, and there are no variables. And if you look at the same integral, this is the identical same integral, integral a to b, now I say f prime of t dt. Again, according to the evaluation theorem, the way we can calculate this integral is to use any antiderivative of capital F prime. So F is an antiderivative of capital F prime. So then we just do f of b minus f of a. So even the integral from a to b of f of t dt is equal to this constant. So even this integral that's in terms of t, again, gets us back to the same constant, f of b minus f of a. So whether I'm doing integral a to b f prime of t dt, integral a to b f prime of x dx, integral, any letter that you want other than a and b, since those are being used, integral a to b f prime of, s ds, it's all the same. If it's a definite integral, they're all going to evaluate to a constant, and a constant that we can figure out using the antiderivative of the integrand. So here, no matter whether I'm integrating f prime of t dt, integrating f prime of s ds, f prime of x dx, they all come back to f of b minus f of a at the end of the day. So, I'll mention this some more. We'll talk about this a lot, but it's a little strange, but it's very much like the index in a summation that gets replaced with actual numbers, and there's actually no index in a summation. So sums add up to a number. There's no index there. So I wanted to do a total area example. So here, this is not asking for net area, it's asking for total area. And so I just wanted to explain what's total area. So the total area is basically, what it sounds like. It's the area that's above the curve, above the x-axis and below the curve, plus the area bounded, by the curve below the x-axis. So here we want to know the actual area above and below and add those, as opposed to the net area where we're taking the area above and subtracting the area below. So here we're adding all of the areas. And so in math, what we're really doing is finding the definite integral of the absolute value of cosine x. This is very similar to find the total distance, we integrate the absolute value of v of t dt. Here for the total area, you're going to integrate the absolute value of the function. Now we can truly interpret this integral as an area integral, because everything we're integrating is above the x-axis, will be a positive number, will be an area. So the other reason I wanted to do this example is because, you know, I really want you to be careful when you're dealing with the absolute value. You should be careful when you're differentiating it, and you should be careful when you're integrating it. Here, the biggest mistake that I want you to avoid is to simply ignore the absolute value bars. A lot of times students will just copy down the absolute value bars and just take the antiderivative of whatever's in between the, you know, so here I just write, oh, it's going to be absolute value of negative sine of x, because the derivative of negative sine of x, oh no, I don't think I need a negative, sorry. But see, this is wrong here. I can't just ignore the absolute values and just take an antiderivative. That's, you know, we cannot ignore the absolute value bars. Instead, what we should do is think about the definition. What exactly does the absolute value of cosine mean? What does that look like if we write out the definition? And now you remember the absolute value of blah will be blah if blah is positive. So here, we're looking at the cosine between 0 and pi. Between 0 and 2 pi, cosine is positive. So between 0 and 2 pi, I can just copy down cosine. And the absolute value of blah will be negative blah if blah is negative. So here, if you look between pi over 2 and pi, the original function cosine. So you see the cosine graph goes below the x-axis. So between pi over 2 and pi, the original function cosine is negative. So I want to negate it. So between pi over 2 and pi, cosine is negative. I need the absolute value to be positive. So I'm putting a minus sign here. So just the definition of the absolute value. And now we can do the integral. And so what we should notice is every time the integrand changes, so I'm integrating cosine x, but once you pass pi over 2, it becomes a negative cosine x. Every time the integrand changes, we need a whole new integral for it. So here, I integrate the integral from 0 to pi of absolute value. I break that up. First, I'm going to integrate cosine of x from 0 to pi over 2. So I break up the integral and then replace the absolute value with cosine of x. And then I'm going to integrate from pi over 2 to pi. And in this case, the function will be negative cosine. You see the two different integrands. That's why we have two different integrals. I can't use one integral to integrate cosine and minus cosine simultaneously as the same integrand. Here, you know, the function changes its definition, so I need to break up the integral to take that into account. So this is 0 to pi over 2, it looks like cosine. So that's this portion right here. And then pi to pi over 2, it looks like negative cosine. That's this portion right here. So now it's just, now we use the evaluation theorem. The derivative of sine is cosine, so the antiderivative of cosine is sine. And the derivative of negative sine is negative cosine. So the antiderivative of negative cosine is negative sine. And then we do f of b minus f of a, and I got both terms were equal to 1, so I get 1 plus 1 equal to 2. So that's the total area, and we should contrast this with the net area. So if I was doing the net area, then I would just be taking the derivative of the original function cosine. And here what we see is the area of this portion would be 1. The area of this portion below would be negative 1. Since now it's below, and so those areas would cancel. That's how we can conclude, you know, that this also tells us the net area is 0 here. Since I calculated the area of each section is the same, the area of each part was 1. But that was for the absolute value, right? So the area of this bottom section here would be -1. So yeah, the absolute value, how do we integrate an absolute value? We break it up. We write out the definition of the absolute value and we break up the integral. So this is really, really important to know this technique. You know, like I said, a lot of students, the first thing they'll try to do is just to ignore the absolute value bars here and just start differentiating, finding the antiderivative. And, you know, as I said, that doesn't end up working out because that's just not right. So one last example here to end section 4.3. And so this technically would be fair game for the test, everything we've discussed so far. So here it's still an area problem, nothing new. We want to find the area of the region bounded by the function g of y equals 4 minus y squared, y between -2 and 2 in the y-axis. So what's happened here is we now have not a function of x, we have a function of y. What does that mean? The inputs are the y variable on the vertical axis are the inputs, and the output here, g of y, this equals an x value. So for any y value, we can find, you know, plug in the function, it'll spit out an x value. And here, 4 minus y squared, the graph here looks like something like this. It's like a parabola, but on its side. So just y squared by itself would look like this. This is the graph of x equals y squared. So here, look, x has to always be greater than or equal to 0. And so if you hit it with a minus sign, it'll flip over, and adding the 4 shifts it. You know, so here, we want to find the area of this region. So now I want the area of this region. So in this problem, so this is a 2 and this is a -2. In this problem, we basically want to take the procedure we've used before to find the area under the curve and use that procedure here. The only difference is the role of the x variable and the y variable has changed. You know, before x was the independent variable, x was the input, and y was the output. Now y is the input and x is the output. So basically, we're going to now do to the y-axis what we did to the x-axis before. So what does that mean? I'm first going to start by partitioning the y-axis. I want to partition the y-axis between -2 and 2. So here's the graph. And what do I mean by partition? We're dividing the y-axis here into little subintervals of, you know, some very small width. Here you have n subintervals where it's, you know, the top number minus the bottom number divided by n. And then we're doing the same procedure. We're finding one subrectangle. So then I find a subrectangle. And here for the subrectangle, we want to calculate the area of the subrectangle. And, you know, it's really important that you just follow the procedure and the story, you know. Here, for this subrectangle, finding the area, well, what's the area of a rectangle? Right? It's height times width. So I'm just following the story. So here, if I look at this, the area of this subrectangle would be height times width. The height, you can see, is delta y. So here, height is delta y. Now the width is literally this horizontal distance, which corresponds to x. You know, at any point here on the curve, the width would be this horizontal distance, which is x. But x equals 4 minus y squared. So here it's not wrong to write the width as delta y times x, but we want everything in terms of y since we have partition the y-axis. Since we have the height is delta y, and y is our independent variable, y is the input variable here, we want everything in terms of y. So instead of writing x, I write x in terms of y, and here we know x equals 4 minus y squared. So I'm able to write down a formula for the area of one of these strips. And that allows me to build the integral. So here's how the logic works now. This expression, 4 minus y squared times delta y, that's the area of one of these Riemann strips, these rectangles. What I want to now do is calculate the area of every rectangle starting from -2. Starting from -2, I'm going to calculate the area of every one of these rectangles, and I'm going to add them all up. That's what this big S symbol here in the integral is telling me. We're going to add them all up, start at -2, and stop at 2. So for this example, it's really important that you're able to come up with the expression for the area of one of these sub-rectangles, and then from that expression, build the integral. I'm copying down the 4 minus y squared dy, the delta y becomes the dy, and then the -2 to 2, that's from the bounds. And we always go from the small number to the large number. So on the y-axis, we're going from bottom to top. On the x-axis, we typically go from left to right when we're trying to do an area calculation. So for this is basically the most important part, that you're able to sort of analyze this situation, partition the y-axis, create a little strip, realize the height of the strip is delta y, and the width is 4 minus y squared, and then build an integral that represents the area. So this is the definite integral -2 to 2, 4 minus y squared dy. You should tell yourself this story, right? That's the width times the height. That gives me the area of the subrectangle. And now add up all the subrectangles from -2 to 2 to give us the exact area. That's exactly the story of this integral and the narrative, the story you should tell yourself. And now we can use evaluation theorem. I just need to find an antiderivative of 4 minus y squared. So here, 4y minus y cubed over 3 is an antiderivative. We can differentiate that to check. And then I did f of b minus f of a and simplified the answer. So this procedure of being able to construct this area estimate and then build the integral, that'll be really important in Calc 2. Not as important in Calc 1, but definitely, it's important in Calc 1, it's really important in Calc 2. And my suggestion to you is to draw the rectangular strip. That really helps me to figure out what's the area of the rectangular strip and also what are its bounds. So here, this strip has to go from -2 to 2. And the area of the strip is delta y times the width, which is 4 minus y squared. So this ends the discussion of section 4.3 in the evaluation theorem, which is fundamental theorem of calculus part 2, which is fair game for the exam. But now let me start talking about fundamental theorem of calculus part 1, which will be fair game for the final exam, but not for exam 3. So the fundamental theorem of calculus has 2 parts, part 1 and part 2. We've talked about part 2, so now I want to talk about part 1. Yeah, it's a little confusing, but it's kind of like a prequel. So one thing I should mention about the fundamental theorem of calculus part 1 is typically when it's introduced to students, there's 2 things that happens in the fundamental theorem of calculus part 1. First, new notation is introduced. And then second, a new differentiation formula is introduced. So typically, when I show students fundamental theorem of calculus part 1, if I just show it to them right away, it's confusing because there are 2 things happening that are new that we have to work on. One is the new notation, and then the other thing is the new differentiation formula that's given to us. So here, what I want to do is do it piece by piece. So first, let me talk about this new notation that's introduced, and it's a integral representation of functions. This is a way to use, given a function, this is a way to use the definite integral to create a new function. We're going to use the definite integral of the given function to create a brand new function. Okay, so let's build up to that. So first of all, I just want to remind you that in a definite integral, an integral with bounds, the variable of integration is considered a dummy variable and is mainly a placeholder. So here's an example. Take a look at this integral. I integrate x, so from 0 to 2. So definite integral of x dx from 0 to 2 is, according to the evaluation theorem, our fundamental theorem of calculus part 2 will be x squared over 2 from 2 to 0. You plug in a 2, you get 4 over 2. This integral is a really complicated way of writing the number 2. Compare this with the integral of theta d theta from 0 to 2. Here, nothing changes because we say d theta here. We treat theta as the variable, as the unknown. We know that the derivative of theta squared over 2 with respect to theta is theta, so that's an antiderivative, and evaluation theorem says we could use the antiderivative here to evaluate the integral. We get it's equal to 2 again. So at the end of the day, these two integrals are identical. The fact that one integral is in terms of the x variable and that the other definite integral is in terms of the theta variable does not matter. This can be any letter you want. This is the same as the integral from 0 to 2 of s ds. It's the same as the integral from 0 to 2 of t dt. It's the same as the integral from 0 to 2 of smiley face d smiley face. And I hate to do that. So yeah, in a definite integral, the actual variable of integration is like the index in a sigma notation. It's not actually there. It eventually gets replaced by the bounds of integration. It disappears. Okay. So now what we're going to do is we're going to play a sneaky game. Instead of having a constant up here, let's put a variable. Let's have something in there that's not constant. So instead of an integral from 0 to 2, let me do an integral from 0 to blah, where blah is allowed to change. It can be anything we want it to be. Okay, so here's the setup now for this new way of expressing functions. We're starting out with some function f of t. T, that's not a typo. That's the letter t, okay? It doesn't matter. It's just the input variable. So f of t is some continuous function, and pick some number, some fixed constant in the domain of that function. So this is our starting point. Give me a function and give me a number in the domain of the function. Now I'm going to create a new function, and that function is going to look like this. The integral from a to x, this is not a typo. This is an x, a variable, of f of t dt. Remember, this is the t dt is not a variable. The t dt is just a placeholder. The only variable here is the letter x. Compare or contrast this with integral a to b f of t dt, where b is a fixed constant. This integral here, this definite integral a to b, is itself a constant. A is a constant, b is a constant. When we evaluate this integral, it'll give us the net area. However, this integral, a to x, f of t dt, that's going to give us something with the variable x in it. When we evaluate, suppose f did have an antiderivative. suppose the antiderivative of little f, suppose this was equal to, suppose here we were doing, suppose this was equal to f prime of x, of t, excuse me. See, I did it. So suppose this was the integral from a to x of f prime of t dt. Then fundamental theorem of calculus part 2 says this will equal f of x minus f of a. You see, on the right-hand side, the only variable is the letter x. There's no letter t. So this is the new thing that I want you to just take a second to get used to. Look at this thing and see how it's different. How it's different is this upper bound here is a variable. It's not fixed. That's how it's different. Up until this point, we've had a constant up here. And the whole definite integral was just a constant. Okay, so here it is. Here's our new way to express functions using the definite integral. For example, here I define g of x to be the definite integral of the function f of t dt from a to x. Here, whatever goes here would go here. G of smiley face would equal integral a to smiley's face f of t dt. So if you pick a number for x, then I plug it in for x, and then we can calculate the definite integral using a Riemann sum. So here, we've got an input-output machine. The input is the x variable. You give me the value x, I'll plug it in right here in the upper bound, and then using Riemann sums, I'll calculate this entire integral, and so that'll tell me what the net area is, and I'll spit that back out as the output for the input. There's your input-output machine using a definite integral. So using this new thing we created, we found a way to use that to now define functions. So the input is this upper bound of integration x in this example. The output is the value of the definite integral a to x. So here g of x represents the net area of the function f of t for t between a and x. So I put a picture of that. You can see here's what the picture looks like. So here I randomly picked a function f. So here's just some random function f of t. So here's my t-axis. And now I'm defining this new function g of x. So here, remember, a is a fixed constant, but x here is allowed to be a variable. And for any fixed choice of x, so suppose I say x equals 2, then g of 2 would represent this area in this case, because the function's positive. G of 2 would be the area between a and 2 under the function f. So it's kind of a different way of creating functions that we haven't done before. G of x is like the area, the net area function, if you want to call it that. Whatever x I put in here, g of x will equal the net area, below f of t between a and x and bounded by the t-axis. So as I said, x is allowed to vary. The only variable here is x. T is just a placeholder. And we can use any letter we want. We don't have to use the letter T. We can use any letter we want other than X. We've already used X for something. X is being used as the upper bound, and that's it. We can't, again, use X in some other, role. So here, integral a to x f of t dt, that's the same as the integral a to x f of theta d theta. That's the same as the integral a to x f of, smiley face d smiley face. So here we can also write g of x this way or this way. They're the same function. And so this is the part where you have to remember this t dt here in this definite integral, this theta d theta, they're dummy variables. They aren't even there. They're just placeholders. When we actually find an antiderivative or calculate the Riemann sum, they get replaced with numbers that are coming between, from between a and x. So yeah, we can write g of x, as integral a to x f of theta d theta, integral a to x f of s ds, integral a to x f of smiley face d smiley face. They're all the same function. We're just playing a game with the dummy variable. So I will warn you, the one thing we do not want to do, if I have an x up here, I then don't want to also have an x as our dummy variable in the integrand. So now x would be, in two different places, serving two different purposes. For example, here, if I wanted to calculate g of 2, the way our math works is I'm going to replace the symbol x with the symbol 2 wherever it occurs. So I get a 2 up here, but I also get a 2 here as the dummy variable. I write integral 0 to 2 f of 2 d2, which is total nonsense, right? F of 2 d2, that's not even math. That's just, graffiti. So here, be careful. We don't want to write that. And be careful. If I have an x up here, I cannot then also have an x down here. I just need to use a different symbol. T, S, theta, smiley face, whatever, just not x. And in general, whatever variable I have up here, I can't repeat that in the integrand. And this is the most common mistake I see. So the most common mistake is students will write integral a to x, f of dx. And it's a totally normal mistake to make because up until now, every integral has been f of x dx. And then now we suddenly go, oh, no more f of x dx, put the x up on the upper bound and make all your integrals f of t dt or f of theta d theta, or just not f of x dx. So yeah, it is confusing, So here, let's look at some examples. Here I pick f to be 1 over t and a to be 1. And so here we have this new kind of function. Here, the x right here, that's the input. So for example, you say, suppose I give you an input of 2.7. Then g of 2.7 has a geometric interpretation. First of all, g of 2.7 would be this integral here from 1 to 2.7, 1 over t dt, something we can calculate using Riemann sums. So that's really important to keep in mind, that there's a input-output structure in place here. You give me a number, I can calculate this net area using Riemann sums. And I can interpret g of 2.7 as being the exact area, of the region bounded below 1 over x for x between 1 and 2.7 and the x-axis. And so now you might say, no, it's not x, they're using the t variable. And so then I say, okay, or you can say it's the exact area of the region below 1 over t, t between 1 and 2.7 and the t-axis. It really doesn't matter. Here, the x variable, whether I write x or t, they're just the input variable. We've labeled it x, but really we should just call it the input variable. It's really f of input variable equals 1 over input variable for input variable between 1 and 2.7. That's really what the function looks like, f of input variable. In this setting here, if we're giving physical meaning, or if you say x is a spatial variable and t is time, then of course in the application we'd have to be careful and respect the variables. But here, if you're just saying I have a function f of x, well then that symbol x isn't necessarily important. It's just a placeholder for being an input position, an input value. So here's a really easy example that we would never do. Let f of, so this is a typo, this should be t here. Let f of t equal 1. and a equal to 0, and I define this is an integral representation of a function, I define g of x to be the integral from 0 to x of 1 over 1 dt. So this is a stupid example because here we can calculate the integral. Here the integral of 1 dt would be t, and then I do f of b minus f of a, so from x to 0. And so when you plug in the x, you get x and then minus 0. And so this integral evaluates to x. This is a really complicated way of writing g of x equal to x. And why would we do that? We wouldn't. What I wanted to show you was an example of writing a function in integral representation. We could do it with all our functions, but we especially want to do it for functions where we don't know the antiderivative. For example, 1 over t, I don't know the antiderivative. This would be the only way to express this function. I can't really replace this integral here because we don't have an antiderivative for 1 over t. Some of you that have had calculus are saying, well, natural log, that's an antiderivative of 1 over t. The next question is, what's the definition of the natural log? And this integral here, that's the definition of the natural log. All the natural log is it's this integral, and we've just given a special name to it, and then people pretend like, okay, I don't remember that it's an integral. Now I just treat it like a regular function. You know what I mean? So here's another famous example of a function that does not have an antiderivative, and the only way to express it is in this integral form. So this function, sine of t over t, here let a equal to 1, and we define this function, it's called a sink function, like your kitchen sink, but it's sin and then the letter c. So that function, this is the only way to represent this function, because sine of t over t does not have an antiderivative. Sine of t over t is what's known as non-algebraic, and it does not have an antiderivative. So here, this function, this is the only representation of the function. And how does it work? You give me an input value of x, like x equals 2. Then using Riemann sums, I calculate this integral 1 to 2 of s sine of t over d, and then I spit out that net area as the output. So the input is 2, the output is the net area g of 2. And why do we want to do stuff like this? For example, functions like, this one right here, or this one right here, the only way to express these functions is in this integral form, because not every function has an antiderivative. All right, folks, here is the fundamental theorem of calculus. Woo! So fundamental theorem of calculus has 2 parts. Part 1 says, if we define this, function using this integral representation. So here's one of those weird integral representations of functions. Remember, the only variable is the variable x. So because this is a calculus class, and you say, here's a function of x, the first thing we ask, because this is a calculus class, is how do you find the derivative of this function of x? So the fundamental theorem of calculus part 1 tells us how to take the derivative of one of these weird integral representation functions. The derivative of integral a to x f of t dt is just f of x. So what we should kind of notice is that the derivative and the integral basically canceled out, and what was returned back was the original integrand in the correct variable. We didn't write f of t because there's no t variable. The only variable here is x. So here, the derivative and the integral kind of canceled out, and it just returned back the thing we were integrating. That's what you should see here. 2 things. First, we've got this weird definition of a function. That's one thing you should notice. That's something new that we haven't seen before. And what's the theory? X is the only variable, and that's our input. remember, t is what's known as a dummy variable. So here, the dt, that's a dummy variable that's not really there. It's an illusion. And the second thing now is you should see that the fundamental theorem of calculus part 1 has given us this derivative formula. So we had chain rule, product rule, quotient rule. Now we have this, how do you take the derivative of a function that's represented as an integral? So that's what ultimately you should see fundamental theorem of calculus part 1 as. It's a derivative formula for functions that are defined in this weird integral fashion. So defining functions like this is basically, the entire topic of chapter 5. So when we go to chapter 5 next week, or week after next, we're basically going to spend the whole time looking at weird functions like this. Okay, so take some time just to get comfortable with what that function looks like. And in particular, take a look at this picture help. So of course, this is just one example, but this gives you the idea that we're creating a function that basically, keeps track of the net area of another function. That's all it does. It's just keeping track of the net area of some other function. It's a net area function for some other given function. Okay, so the second part of fundamental theorem of calculus, and another way to say that the derivative of integral a to x f of t dt equals f of x is to say that g of x is an antiderivative of little f of x. So you should think about what that means. And so part 2 we've seen, this is a shortcut for how to evaluate definite integrals. If capital F is an antiderivative of little f, then the definite integral of little f from a to b can be calculated as capital F of b minus capital F of a. So we're using the antiderivative of the integrand to calculate. So that's the antiderivative of the integrand to calculate the definite integral, of this function little f. And so part 2 is fair game for exam 3. Part 1 is not fair game for exam 3. Some comments here. The proof of part 1 uses the extreme value theorem and the squeeze theorem. And those are the real reasons we studied extreme value theorem and squeeze theorem. Squeeze theorem is also important for limits. And the proof of part 2, which is the book also calls the evaluation theorem, which is what's covered in section 4.3, uses the mean value theorem. And this is the real reason we studied the mean value theorem so long ago. Not all of those artificial problems that we did, in section 3.2. This is really one of the main reasons. So a couple of comments here, and I'll stop. If we define g of x to be this integral from 1 to x of 1 over t dt, then according to this fundamental theorem of calculus here, the derivative, you see here this derivative formula, the derivative of the integral from 1 to x of 1 over t dt will just be 1 over x. So here, the FTOC part 1 tells us that the derivative of this weird function, 1 over, so when I say this weird function, let me describe what weird function I'm talking about. The weird function is the definite integral from 1 to x, 1 over t dt. The derivative of that function is 1 over x. So that function is the antiderivative of 1 over x. So this is one of these mysteries that we still had to solve. One thing we never figured out was what's the derivative of 1 over x. And so this is, one reason why the fundamental theorem of calculus is so important. It allows us to finally answer the question, what's the antiderivative of 1 over x? And this function here, integral 1 to x, 1 over t dt, we build this function, and this function is defined as the antiderivative of 1 over x. We don't call it g, we now give it a special name. So instead of calling it g of x, we give it the special name. Let me change my here. So instead of calling it g of x, we call it ln of x. And so, this is why fundamental theorem of calculus is so important. By using this type of weird integral, defined function, using the definite integral to define this new function g of x, we're able to create a function that turns out to be the antiderivative of 1 over x, called the natural log. And we end up discovering a whole new family of functions, the logarithmic functions. And we look at the inverse of the logarithmic functions, which are the exponential functions. And so now we get this whole new class of functions known as exponential and logarithmic functions, which we can use to do math with. Specifically, one of a big application of the exponential function is to solve differential equations. That's kind of part of the reason why you're taking this calculus class at all, because you take Calc 1, Calc 2, Calc 3, and then you take differential equations. And in differential equations, we solve those differential equations using exponential functions and natural logs, which, are created here in Calc 1, which find their, beginnings here in Calc 1. The origin story of the exponential function and the natural log function starts in Calc 1 at the fundamental theorem of calculus. That's why it's so important. So this next comment, I'll actually continue next time. So remember, you can think of fundamental theorem of calculus part 1 as a differentiation formula. Specifically, if you focus on this part, it's telling you how to do a derivative. And if you remember back to derivatives, anytime we learned a derivative rule, we also wanted to learn how to do chain rule version of it. And so here, what I've written here is the chain rule version of fundamental theorem of calculus part 1. And I'll get into the details on Monday. We don't need to worry about this right now, and especially keeping in mind this material specifically here. Fundamental theorem of calculus part 1 will not be on the exam next week. So I'm not going to get into it. We've already done a ton of theory. Okay, so things for you just to kind of kick around in the back of your head is to think about this new and alternate way of defining functions using the definite integral, where x is the only variable, and keeping in mind the t is a dummy variable, and then the idea of now how do we take the derivative of this new, integral defined function. So that's kind of the whole point of the fundamental theorem of calculus part. Introducing these new integral representations, and then how do you take the derivative of these integral representations. All right, I'm going to stop right here.